Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. And in this video I'm going back to galaxies, but I'm looking at a particular law that relates to spiral galaxies basically. This is the Freeman Law. Now, like with all my other galaxy videos, maybe the planet videos as well, what I'm going to do at the beginning is just kind of recap what galaxies are, just in case you've come across this video and you haven't seen my previous ones, or it's just a recap on what galaxies are and a few different sorts. If you know all of that, then skip past that and get straight into kind of the Freeman Law about midway through. So just as a recap then, galaxies are these enormous systems of stars, gas, dust and dark matter. They're held together by gravity, so they're gravitationally bound. And there's various different types, and different types have different ratios of stars, gas, dust, dark matter. Some have more stars, some have more gas, some have a lot more dark matter, and it depends on the type, but they're basically composed of these components here. And they come in lots of different sizes and shapes, and most of these are disk-like galaxies that I've got here. You've got some irregular ones that don't fit a regular shape, disc-like ones, elliptical ones, ones that are kind of in between, ones with spiral arms, and they can be small dwarf galaxies. You can have massive elliptical galaxies or even massive spiral galaxies. So they come in a whole range of sizes and shapes. They're not just, one type basically. So if we go to the Hubble classification system, it normally looks like this tuning fork here, and it helps us kind of classify galaxies, but it also helps understand a little bit about the evolution as well. Now, spiral galaxies or disk-like galaxies sit to the right-hand side, where you've got the two branches of the fork. The top branch is your normal spirals. They have a spherical central bulge, and then the lower one is barred spiral galaxies, a bit like our Milky Way. They have a bar in the centre as opposed to a spherical bulge, and sometimes you see an intermediate one, so you might have three branches there, and that means that they are kind of in between. They don't have a full bar, they have a weak bar basically. And then you have your elliptical galaxies, and these are classified purely on their shape, so how elliptical they are. They're featureless, they don't have spiral arms, they're not disc-like, so again they're more kind of round as opposed to flat and disc-like. I've got lots of videos explaining the differences between the two. We're not interested in ellipticals for this particular video anyway. We're more interested in the spirals. So the Freeman Law concerns spiral galaxies, and that's these group here basically. So the ones are kind of highlighted. So your disk-like galaxies, your spiral galaxies, it relates to the Freeman Law. It doesn't relate to your ellipticals because they're slightly different in their composition and their structure basically. So what does it actually state? Well, it states that spiral galaxies, well, their disks anyway, have a nearly constant central surface brightness. So if you look at the central part of a galaxy, like the central bulge, then that central brightness is pretty constant throughout the different galaxies. Again, what we're basically doing is we're only looking at spiral galaxies, so it doesn't concern those elliptical ones. Now, that value, it was originally proposed that this central region, it was around about 21.7 magnitudes per arcsecond squared, and that's in the B band. So if you take that central part, that's the kind of expected brightness in that particular band we would expect as a function of area. So the B band, if you're not fully aware of that, it's in the optical part of the spectrum, and it's centered on the blue light. So if you know anything about photometry, and lots of telescopes will have different filters so they can actually look at different things, but this particular Freeman Law is focused on the B band. So you're looking the optical part of the spectrum centered around blue light there. So there you've got along the bottom your wavelength, and then essentially how much light it lets through. So if you have a blue filter, it's only going to let blue light through. So we're only looking at the galaxies in blue light for this particular law. So the first part there is then your central surface brightness, so mu0, and then on the other side there, that's your units, and that's normalized per unit area basically. So that's how bright it is per unit area in the central part. That's magnitudes per arcsecond squared. Now, you've got your spiral galaxies here. What it's basically telling you is that this central brightness is independent of their size or luminosity. So you can have a smaller galaxy, a bigger galaxy, and that central brightness is near enough going to be the same. That's what the law states basically. So Smaller galaxies and bigger galaxies have a very similar central brightness, irregardless of how bright the actual galaxy is or its actual size. So again, if we then go back to the Hubble tuning fork classification diagram, all those galaxies there, this law states that they have very similar central brightness, which is in and around that value, the 21.7 magnitudes per arcsecond squared, basically. Now, what does this suggest? Well, it suggests that there might be a common formation or evolutionary process for spiral galaxies. I'm not going to go into the details of that. I've got some other videos that actually look at the different theories for galaxy formation and how they might form. But this is one idea here where you get smaller spiral galaxies slowly merging and they would grow in size to get your bigger ones. And I've got a video on that basically, but that's one idea. And it might suggest that spiral galaxies have a common root for formation. And if that's the case, that's why they might all end up having the same central brightness. However, this was a fairly old observation, so it was in the 1970s. And later surveys, so more recent surveys of galaxies, have actually showed that there's variation from this Freeman law. It's not absolute. It's fairly general, so it doesn't work for all spiral galaxies. And part of the reason for that is that your older surveys, your telescopes, your surveys were not as sensitive, so your very low brightness galaxy, so low surface brightness galaxies were missed in those early surveys. So here we've got kind of very low luminosities or low surface brightness galaxies, and they're difficult to see. So until we get better telescopes, we basically didn't see them. So there's a selection bias there where they weren't in the survey. So hence when you looked at the data, you then come up with this law and it fits what you've got. But now we have these fainter galaxies that don't fit that. So these are not quite the same now. So later surveys have actually showed that there's variation due to picking out these much fainter galaxies. But it's still a pretty good reference point for large spirals, because large spirals are easy to see, they're bright, they're luminous, and it's still a very good reference point for those larger spirals that we can actually see. It's more the lower end that it deviates away from. So it's still good at using as a reference point to identify whether a spiral galaxy is low or high surface brightness. So we can categorize these galaxies as low or high surface brightness, and using the Freeman value can help us actually put them in one or two of those groups there. So still a very good reference point, but it's not absolute across the board as it was originally thought to be. So if you've got galaxies that have a very prominent central bulge, so this might be an SA type. Now that is kind of the older spirals. So it would be on the left-hand side of the actual Hubble tuning fork, basically. So these are spirals that have evolved, they've been around for longer, and actually in time they get a bigger bulge. So they can actually have a much brighter central brightness essentially. And that diagram there is just the actual not the central, but it's the surface brightness as a function of the distance from the center of the galaxy. And you can see that in the center part, it actually increases. You'll notice that actually the magnitude goes down, but it goes up on the graph. That's because magnitude is inverse. So they're much brighter in the center than they should be, and that's because they have these very prominent bulges. And as they evolve, so if we go from like the SC to the SA, then they get larger bulges basically, and that's kind of why they deviate. So it might be that actually on the other side, the Freeman law suits those better than it does the actual older spiral galaxies. So in the SD type, so they're the ones these are essentially the younger ones, or we call them late type because they're actually on the right hand side of the diagram. It's backwards, I know. And what happens here is they have a very weak bulge, small bulge, and this does not contribute significantly to their surface brightness profile. So if you have a look at the profile here, you've got the surface brightness as a function of radius, and you can see it doesn't deviate away from like an exponential profile. So in this case here, this would be fairly suitable. So yeah, in these galaxies here, we can treat the whole disk as just a single exponential disk. There's no different component in the centre for the bulge because it doesn't outshine the rest of the galaxy. It doesn't just suddenly get brighter. So these, again, depending on the evolutionary phase, would probably be better. And these ones here are the ones that are likely going to have smaller bulges. So on the right-hand side of the Hubble tuning fork, these are younger spirals. Again, we call them late type, but these do have smaller bulges and they will kind of grow in size as they evolve, in time essentially. So thank you for watching. If you enjoyed the video or find it helpful, then do consider becoming a member of the channel. Obviously helps support the channel, but we do have some extra videos in the member section as well. So thank you for watching.